This video will review rocket and friction problems. These are the same type of problems that came off of the force problem set number 3. So if you're looking for more examples of these problems, you can go to that worksheet. You either have it in hard copy or it's posted online in one of the previous assignments. But I took these questions from that worksheet and just changed the numbers around a little bit. So with the rocket problems, the thing that I always suggest starting with is kind of drawing a picture. I think that helps just kind of visualize the different forces that are at work and helps just kind of keep everything organized. So here's my little rocket. As you know, I'm a fantastic artist. And here's the fire, okay? The flame to propel that rocket. So we are dealing with a 100 kilogram rocket. How much force is necessary to accelerate a 100 kilogram rocket at 10 meters per second per second? So these are, unless it says otherwise, we're going to assume that these are occurring on Earth. So if we're just dealing with a 100 kilogram rocket and we want to shoot it straight up into the air and we want to accelerate it at 10 meters per second squared, we can figure out what force would be necessary to do that. I'm going to label that FRO, force of rocket. Okay, that's just an abbreviation I made up for force of rocket. So force of rocket will be 100 kilograms times 10 meters per second squared. That would be, just in order to accelerate this rocket, how much force we would need. So FRO is going to equal 1,000 newtons. However, we have forgotten that we also need to deal with something that pulls the rocket downward. Its weight, or its force of gravity. So we need to figure out its F of G, force of gravity. In order to do that, we need to remember that A of G, acceleration due to gravity, is 10 meters per second squared downwards. This problem works out nicely with the math. If we take 100 kilograms times the 10, oh, look at that, it's going to be the same. It's going to be another 1,000 newtons. Those are zeros. So the force of gravity alone is 1,000 newtons. And then in order to accelerate it at 10 meters per second, we need another 1,000 newtons. If we only gave this rocket 1,000 newtons of force, is this rocket going to move? No. Because if we give it just 1,000 newtons of force, that's just enough force to counteract the downward force of gravity, to take care of this force. But we need to not only take care of that force, but we also need to give it enough force, right here, to get it going 10 meters per second upwards. So the net force, or the thrust, another word that we can use is the thrust, the amount of power, the amount of force that we need to give this rocket is going to be force due to gravity plus force of the rocket. So that's going to equal 1,000 newtons plus 1,000 newtons to be a total of 2,000 newtons. That would be your answer for how much force is necessary to accelerate this rocket. A really simple way of doing this is, since we know it's on Earth, whatever this rate of acceleration is, we add 10 to it, right? If we add 10 to that because of gravity, so we had 20 meters per second squared, and multiplied this by our mass here, we'd have 2,000. So that's another way that you can do it if you don't like to show all this work and go through all of that. And if this makes sense to you, do that. That's a little shortcut that I'm going to show you, but do whichever way you're able to do consistently. Do a couple practice problems, and if the shortcut isn't working for you, don't use the shortcut. For this problem, it should say number 2, but my numbering got messed up. We've got a 50 kilogram rocket that generates 1,000 newtons of thrust. How fast will it accelerate? So, drawing our picture, here is this rocket's even uglier. Here is my rocket. It is a 50 kilogram rocket. And the thrust, or the net force, is going to equal 1,000 newtons. How fast will it accelerate? So we are interested in its acceleration, which we don't know. We do know the downward force of gravity here. If it's a 50 kilogram rocket and A of g equals 10, then F of g is going to be 10 times 50, or 500 newtons. Now, to bring us back a step here, we need to remember this equation right here. So if net force is equal to force of gravity plus the force of rocket, we have net force. We have F of g. So all we're left trying to find out is the force of the rocket. So if F of g plus F of RO equals net force, we can just subtract force of gravity from net force to find the force of the rocket. So 1,000 minus 500 leaves us with 500 newtons. That tells us that the force that the rocket needs, or the force that the rocket has left over after we've taken out the force that is spent just to beat gravity, is it's got another 500 newtons to actually accelerate it. So if the force of the rocket is 500 newtons, 500 divided by 50, we're again going to get an acceleration of 10 meters per second squared. Once again, that's just accidental that ends up being 10 meters per second squared, just like the acceleration due to gravity. My numbers randomly ended up working out like that, so don't get thrown off by that. In both of these cases, what we need to remember is this right here, that we're adding the force of gravity and the force of the rocket, which tells us the total force that the rocket needs to be able to not only beat the force of gravity, but also send the rocket accelerating up into space. So if we are, given this one, force of gravity and force of rocket, we can add them together and solve for net force. If we're given net force and force of gravity, we can subtract them to find the force of the rocket and then simplify down to the acceleration. In both of these cases, we're using the same equation. We're using that same kind of setup there. We're just approaching it from different angles. Okay. These numbers are easy to kind of manipulate. You can take both of these examples, change the numbers around, and give yourself some new practice problems. If you create some practice problems and want to send me your solutions, I'm happy to take a look and see if you did them the right way. Here is a friction problem, our third number one. So once again, I suggest drawing it out. Here's my object. It's a 10 kilogram object. It has 20 newtons of friction, and I'm going to label that FR, friction. And it's going to be pushed by 50 newtons, and I'm going to label that the push. How quickly will it accelerate? Well, as we know, when two force vectors are moving in opposite directions, so since they're both pushing in on the box, or if one was pulling away and the other one's pulling in the other direction, we are going to subtract. So 50 newtons minus 20 newtons leaves us with 30 newtons. So that is what is left over of the force of our push after friction acts on the box. So 30 newtons, if we're going to set that up to mass times acceleration, 30 newtons equals 10 kilograms times A. Divide both sides by 10. And acceleration is 3 meters per second squared. Right? 30 divided by 10. So that's how quickly that object will accelerate. One thing I would like to point out is if the friction is ever larger than the push, that object won't move. And we've all encountered that before. You've come up against a car or a desk or something that's really, really heavy, and you push it from the side, and there's too much friction. You can't move that object. It has too much static friction for you to move. That means that the friction is larger than your push. So if the friction, instead of 20 newtons, was 100 newtons of friction and a 50 newton push, then you're not going to move that object. Its acceleration is 0. Another thing, a comparison that we can draw here is that these friction problems are essentially just rocket problems that are horizontal, right? Rather than dealing with gravity and acceleration due to gravity, here we just have a set amount of friction that you are given. So rather than gravity, you are given an amount of friction acting on an object. And this works now horizontally, so this way, rather than vertically, up and down. But as you can see here, this was the total amount of force. We subtracted friction, and we're left over with what is able to push the object. That's the same thing that happened right here. Net force subtracting the force of gravity, the weight, which essentially is the friction down here, and then what is left over to accelerate the rocket. If what I'm explaining here is confusing you, just don't even worry about it. I'm just trying to draw a little comparison between the rocket problems and the friction problems, one of them being vertical, one of them being horizontal, but essentially you are solving the problems in the same way. My suggestion to you is you take these problems, try to solve them on your own, and compare your answers to mine, watch the video a few times, try to make some sense of it. If you are confused, as always, please get in touch. Please come see me in a study hall or send me an email and we can figure out a time to meet. Thank you.